Welcome everybody to your favorite YouTube video series, Watch Your Professor Grade. This is homework 7 and we've got 6 new contestants. Let's jump into it. So, first problem, prove that if we have 3 real numbers, A, B, and C, then, this is saying the distributive law holds. So of course in class we were able to write down what the real numbers were, right? They're equivalence classes of Cauchy Q sequences. And so every proof we do trying to verify the real axioms, or the field axioms for the reals, we want to reduce it down to the rational numbers where we already know the field axioms hold. So let's take a peek. All right, we're starting from A times B plus C, and of course we want to end up at AB plus AC, so that's good. What's not good is we haven't started with any words, right? We had this rule that we weren't going to start sentences or new clauses within a sentence with math symbols. Well, this is like starting the entire paragraph, even the entire solution, with a math symbol. So we need some words, even if it's just as simple as we have. Something like that is fine, but we need some words at the beginning. Okay, now it looks like we're translating A, B, and C into, I'm guessing the intentions that these are equivalence classes because of the square brackets. That's good. But then we would need Cauchy sequences. Okay, and AN is not a Cauchy sequence, it's just an element. So what we want, all right, in fact, I think instead of starting with we have, we're going to need to set some notation up, right? We're going to say, since A, B, and C are real numbers, there exist, and now we can have A, B, and C ends in the set of Cauchy Q sequences, okay? Such that A equals AN, B equals, B is equal to BN, and C is equal to CN. Okay. Thus, okay, now we can jump in here, and now these are going to have parentheses around them in here. So we know we actually are looking at sequences. Okay? So we would get the product now of this equivalence class times this equivalence class. And on the inside of this equivalence class, we're adding 2 sequences. And so again, we have parentheses here. That's how we add sequences. Now we can multiply these together. And again, this is an entire sequence. Fine. You have an equivalence class of a Cauchy sequence of, right, of these rational numbers, and you just have this multiplication. And now you're right to say, right, that we want to use the distributive property, but it's not the distributive property of equivalence classes. That's actually essentially what we're trying to prove. We're trying to prove, or we're trying to use the distributive property of the rational numbers. Okay, so this would be of Q. And now I know what you're trying to say here. You're really trying to just continue on, right? And we can't do that because literally what this is saying is by the distributive property of Q equals blah, right? And that's not a thing, right? This sentence had to end up here, right? In fact, there's a period that we need to have. So again, by the distributive property of Q, we have, and now you can copy this over here, and that's fine, right? So you say, okay, I have the class of AN times BN plus CN here, close parenthesis, close bracket, equals. Now you can do your distributivity. Okay, again, we have to break this up with parentheses here, and so forth. Now you're breaking it up using the definitions. That's quite fine, that's quite fine, that's quite fine, equals that, period, boom. And then we want to bring this up, as we saw in the video from last week. And in fact, this is such a, I mean, this is happening enough. And this happens to me too when I'm writing. So let me add this in as an issue 25. All right, it's an easy one to fix. when finishing a proof in display mode, you have to hard code moving the proof end symbol, okay, that's that box at the end, up to the previous line. So what LaTeX wants to do when you're in display mode here, like you're using the align environment, is it doesn't want to put this end symbol at the end of this line, but that's where we want it to be. We don't want to waste an entire line with this. Okay, and the code to do that, at least when you're in a 12-point font, which we are, is we say, and this is before, so before the display mode starts, that's fine, starts, enter the code below display skip equals -12 point. Okay, and that will move this box up into this final line. Okay, yeah, obviously there's nothing wrong with it, right? And it's not like you're in the middle of a big paper and everything, and you're wasting all this space. But this is a good habit to get into. Okay, so yeah, obviously if you're working in a different font size, then you need to change that 12 to 10 appropriately, or it'll be not quite right. Okay, so the idea of the proof, right, is correct. We just have a few things we got to work on, the notation, and then properly attributing the distributed property to Q instead of the equivalence classes. Okay, let's go to contestant number 2. All right, looks like we have the same type of problem, only this time we're dealing with the commutativity of the reals instead of the distributivity. All right, so let's see. Note, A equals A dot and B equals B dot for some A dot B dot in CQ. Okay, that's absolutely correct. Right? This is what we were saying in the last one. We want to translate our A's and B's into equivalence classes of Cauchy sequences of rational numbers. And that's what this notation in class meant. Because a real number is an equivalence class. Yeah, so that's fine, but we don't really need it here, right? Like that's okay. Like we know the definition. So we'll just ditch that. All right, since A dot and B dot are sequences of rational numbers, and rational numbers allows commutativity. Okay, so there's a grammatical issue here in terms of allows commutativity, but also just a meaning issue. When we say allows commutativity, like to me, it says, well, it means it's possible, right? It's not disallowed, right? We don't stop it from happening. But the rational numbers are commutative under addition, right? Now, that's something very specific here it's not mentioning. If you say the rational numbers allows commutativity, the question is of what? What commutes? Am I just allowed to write down 2/3 and then 4/5 and write those in any order I want? Is that what you're saying? Or are you saying there's an operation like times in between it or plus in between it? Or minus. Ooh, minus doesn't work now, does it? Okay, and that's the point, right? Like there are some things we can do with rational numbers that are commutative operations and other operations that are not. So we need to be specific. So I think what you're trying to say here is that A and B are sequences of rational numbers, and rational number addition. So addition is commutative. Okay, it follows, well, we're going to say it follows that. Okay, and this is really the key point in the whole proof. And so this is where you actually want to take some time. Okay, and actually if you go back to the previous contestants' work, you'll notice they started with ANs instead of the A dots. And this is an instance where I actually think the AN is a better way to go, right? I would actually change my A dots into ANs here, because what you could then have is I say, oh, well, I have AN plus BN. I can put that together because that's the definition of how we add equivalence classes. I can then add the sequences together because that's how we add sequences. And now this rational number commutativity line, I'll put that down here, allows me to swap AN and BN, right? And I can see it very clearly. So this is BN plus AN. Okay, and then I can undo all this, right? So now unravel. All right, and this unraveling should look basically like what you had up above, right? Or you could just say, by symmetry, right? This is going to equal b plus a either way, all right? The point is if you want to make it very clear how you are using the commutativity of rational number addition, this notation is going to make that clearer, right? You're not leaving anything to my mind as, well, what are you talking about? You're just commuting sequences. Why is that? Like, why can I do that, right? And here, this answers the question. It's because when I add sequences together, I'm adding them component-wise or term-wise, and then, I can swap these because real number addition is commutative. Okay, so maybe make that change. That's going to make this a lot better. All right, let's go to contestant number 3. All right, same problem as last time. And I mean, the very first thing that jumps out at me is this big symbol right here. Okay, and I see it in a bunch of different places. Boom, boom, boom. Okay, and we actually have a rule, right? This is number 20, okay, which is saying we're not really supposed to be using these kind of symbols. Okay. In fact, let me add that to this chart here. That, I mean, we don't have that one specifically yet, but now we do. Okay, so none of these symbols that exist for all the implies arrows are going to be used in formal proofs, with the exception possibly here the implies arrow when we're using it as a limit. A arrow L, right? When you're talking about A converges to L, that's quite okay. But in terms of these sort of logical symbols here that we're using, yeah, we're not going to write those typically in our formal math proofs. So that's number 1. Number 2, you're not actually using the symbol even correctly. What I mean is, even if this was not a formal proof, even if we were just writing this on the board, then what you're writing doesn't make sense. Okay, A plus B equals, that's good, class of A plus the class of B. Absolutely, that is what, right? That's what the real number A means, the class of A dot. The real number B means the class of B dot. And now, when I add two classes together, I get a new class, and they are equal. They are not equivalent or if and only if, okay? This symbol, this if and only if symbol, this equivalent symbol, right? That typically you'd be using between propositions, right? So I'd have some sort of P if and only if Q. This needs to be a proposition, okay? And Q also needs to be a proposition, okay? A dot plus B dot is not a proposition, right? This is a noun. This is an object, right? This is some quantity that we have, and you can't say that a quantity if and only if another quantity. You can only say, oh, a quantity equals a quantity, or equal is not equal, or is greater or less, or is equivalent, but not using these symbols, but you might have later on, A equivalent to B or congruent to B, all right? So you can use that. We cannot use this symbol here. I also notice here then, hey, that's issue number 8, okay? We've got to start using then after ifs. That's it. Okay, fine. Now let's see, if we'd made these changes, A plus equals that equals B plus A. Okay, this is, of course, where the real proof is. Why is it that A dot plus B dot equals B dot plus A dot? Now I refer you to the previous contestant for my suggestion on how to fix this. Okay. Note the next sentence, you're basically trying to say why it's true. You said, by the fact Q is commutative. So first, this is not a sentence, okay? You'd maybe say, by the fact Q is commutative, we have, it follows that, whatever, but this is not a sentence by itself. And also, you don't have elements of Q here. You have sequences. And we haven't proved that Q sequences are commutative, right? So there's one more step, right? You're starting from real numbers. You're converting those into Q sequences. And then you need to convert that, right? You need to convert that. Oy. Come on, eraser tool. Wow. Eraser tool just doesn't want to turn on. There we go. Okay. You're turning these into rational numbers. Okay. In the sense, if I have some A, what do? I say, well, this is, right, some A dot or AN. And then from here, okay, I'm looking just at the AN. Okay, so what do I mean? Let me make this picture more explicit here. In this context, we're looking at A plus B. We convert that into, let's do this like here, AN plus BN. And then from here, right, I want to take this and look only at the AN plus the BN. Okay, of course, there's all the rest of the stuff going on, but the point is that the rational addition is happening at this step, right? Once I put everything together, okay, this is now rational addition. Okay, note again, when you say Q is commutative, under what? We have to be talking about an operation, okay, under addition. Okay, so reduce it down to the level of Q explicitly. All right, let's move on to contestant number 4. Same problem. Given A, B, and R, well, that's already done. We don't have to repeat that. Oh my, what's happening here? Adding 1 on both sides. Well, okay. That would be, assuming this is true. Now, it's certainly the case that this is true if and only if A plus B equals B plus A. It follows that A plus B plus 1 equals B plus A plus 1. Okay. Axiom 2, which, okay, so you're going to use associativity axiom. So you could just say that. In fact, that'd be the right thing. But A plus B plus 1 equals, okay, so you're going to, wait, what did you just do? You swapped the role of A and B. Okay, so associativity doesn't tell you could do that. That would take both associativity and commutativity, which you're trying to prove. And then you get to here, which you already had, right? There's A plus B plus 1 equals B plus A plus 1, and now you recover it. So you have not done anything. And then you subtracted 1 and got back to what you started with. So you started with a statement, and you said, I want to prove this is true. I'm going to add 1 to both sides. Then I'm going to subtract 1 from both sides. I get back my original statement, therefore it's true. Okay, that doesn't, like, you haven't proved anything, right? You've only shown essentially that this statement is equivalent to itself. It's true if and only if it's true. Okay, so watch the other contestants to see how you can improve on this one. Let's go to contestant 5. Okay, it says time for associativity. No, this is distributivity again. Oops. Okay. Yep. Oh, this is a weird thing there. Okay. I'm guessing that you hard-coded this dot instead of using my my macro. So I created a macro for you. So if you do backslash SEQ and then A in the curly braces, this will give you a dot. And that would probably have solved your problem here. Okay, but in any case, you're starting off, yep, you got 3 sequences in Cauchy-Q sequences. Okay, that's fine. Nope. Let's see. So A dot plus is equal to this. No, we can't write this. So these square brackets are not parentheses. Okay, they're not ways of telling you the order of operations here. Okay, these are telling you equivalence classes. So the correct notation would be, well, first thing, it would be this times parenthesis B plus C. Okay, and then when you go to put it together, which that's okay, we can do that, I would have A dot times B dot plus C dot. But the square brackets aren't on the inside because we're not taking the equivalence class of an equivalence class. Okay. Now, what you want to do, the next step here, that you want, like this is what you did, is you say, oh, well, now I can distribute. Okay, but here's the problem. Okay, this, whoop, come on. Oh boy. Come on, Adobe. Give me a little help here. Fine, we'll do it that way. Okay, so I'm going to type in here the problem. Okay, this step, okay, starting with the star, assumes that sequence addition multiplication is distributive, which we haven't proved. You need to reduce, oh, we're going to spell multiplication right, don't we? You need to reduce this down to rational distributivity. Okay, so if you watch how we handled the other contestants so far, you'll see what I mean, where we can turn these into ANs and BNs and get it all down into one, okay? So you need to go in and actually put in these extra steps, okay? Because right now, you're essentially reducing the problem to something, which is good, but it's not something we know is true yet, okay? All right, final contestant. Let's see. This time we have two real numbers A and B, where A is less than B. C is some positive real number. And we want to show that, yes, if we multiply an inequality by a positive real number, the direction of the inequality does not change. All right, let's see. Since A, B, C are real numbers, it follows that A, B, C, da, da, da. Okay, cool. We can turn these into Cauchy sequences. If A is less than B, well, we don't want to say if about something which we already know is true. All right, so we already know that A is less than B. So we don't want to if that. Okay, this is issue number 9. Okay, you can see it right over here. Okay, we don't let if or suppose that which is already true. Fine. We could say since A is less than B, we have B minus A is greater than 0. Now, when you say where B dot minus A dot has a positive tail, I think you mean to say that you're claiming that it has a positive tail as a result of B minus A greater than 0. So it's not where. Okay, that's not the right word here. It's probably you want thus B minus A has a positive tail. Okay, by multiplying by C, we obtain C times B minus A is greater than 0 times C. Okay, so this is problematic because we haven't proved that if I multiply by C, that the inequality is going to be preserved. And that's what you are using right here, right? You're trying to use what you're trying to prove. So this doesn't, we can't do this, right? So this assumes that the conclusion is already true. So that's a problem. Let's see what else you did. Note that since C is a positive real number, C dot has a positive tail. Okay, and so B dot times C dot minus A dot times C dot must have a positive tail. So this is true, and it's what you want to get to, all right? But we need an argument here. And so we know that B dot minus A dot has a positive tail. We know that C dot has a positive tail. And so what we could be doing, right, is we could use the Mc theorem, to argue that there exists, well, you can go out far enough so that both sequences are positive, right? So there exists an n such that if little n is greater than or equal to big N, then C sub n, will I do it? No, C sub n and B sub n minus A sub n are greater than 0. Okay, so this is, well, say this is greater than 0 and that's greater than 0. Okay, so if you go out far enough, right, in both sequences, they're both going to be positive. And now you can multiply them together and you know that those will be positive, right? Because these are just rational numbers. Thus, Cn times, or we'll write it the other way around, right? Bn Cn minus AnCn is positive. Or equivalently, right? Equivalently, we would then have that what you're trying to write up above, right? So B dot C dot minus A dot C dot has a positive tail. Okay, so those are the extra details that we need here. Okay, and of course this line here, right? When we said thus this is true. Of course, this is right. Just since inequalities for Q satisfy the original property as well as distributivity. All right, or well, I should say not that the inequalities, right? So I'll just say since Q addition and multiplication satisfy or are distributive. Okay, so that when I got from the Bn minus An greater than 0 and Cn greater than 0, and I multiplied the Cn by the Bn minus An, the fact that I could write it like so, right, of course I'm using distributivity. All right. And then the fact that I still have a positive here, right, that's using the property we're trying to prove, but for the rationals, right, not for the reals itself. Okay. Let's see, since Q addition, multiplication are distributive and inequalities, whoops. Oh dear. We're losing it. There we go. And inequalities for Q satisfy the original property. Okay. So once you know now that this has a positive tail, right? Well, that's of course equivalent to saying that BC dot minus A. Well, I actually just go back now to your original stuff. BC minus AC is greater than 0, i.e. BC is greater than AC. Okay, so that'd be enough there, which is what you're trying to do at the end. Okay, we just need to fill in these extra details. Okay, everybody, well, we've gone through all 6 contestants. I think we only have maybe a couple more of these things to go, right? So maybe even just one. We'll see. All right, but we will see you next time on Watch Your Professor Grade.